Hey everyone, and welcome to this explainer. Today, we are diving into something absolutely fascinating. We're going to explore the world of swarm intelligence. Now, I know bugs might not be the first thing you think of when designing software, but if you've ever banged your head against the wall trying to scale centralized architectures or struggled with highly dynamic, unpredictable environments, you are definitely going to want to pay close attention to the algorithms we're unpacking today. It's a real game changer.
So think about this for a second. How is it that tiny insects with practically zero individual computing power can flawlessly execute complex routing and scheduling tasks, and they do it without a centralized command server, no master database, no load balancers? Nature has been solving these massively complex NP-hard problems for literally millions of years. Ant colonies find the absolute shortest path to food. Bee swarms evaluate and select optimal new hive locations, and they pull the whole shebang off without a single leader telling them what to do.
Here is our roadmap for today. 1. Swarm intelligence core principles. 2. Ant colony optimization. 3. Bee colony optimization. 4. Escaping the local minima. And 5. Real-world applications.
All right, let's jump right into part 1, Swarm Intelligence Core Principles.
So, swarm intelligence was actually first introduced by Gerardo Beni and Jing Wang way back in 1989. And the whole thing relies on super simple local rules that naturally produce complex adaptive outcomes. There are a few general principles at play, but two are absolutely crucial for our coding models. First up is the proximity principle. This basically means that the individual agents in a swarm aren't looking at some global map. They compute solely based on local environmental variance. It's just a direct behavioral response to their immediate surroundings. Second is the quality principle. A swarm has to be able to respond to quality factors, things like the richness of a food source or environmental safety. When we translate this biological behavior into code, these localized, simple responses naturally create this highly intelligent, emergent global output.
And when we contrast swarm intelligence with centralized machine learning, the differences are pretty stark. Centralized ML relies heavily on pattern recognition from massive datasets fed into a central model, right? It requires serious computational overhead, and it really struggles when the environment dynamically changes on the fly. Swarm intelligence, on the other hand, is entirely decentralized. The intelligence emerges purely from the interactions of the agents themselves, not from top-down instructions. So it's incredibly lightweight, natively scalable, and highly adaptable in unpredictable real-time environments.
Let's move on to Section 2, Ant Colony Optimization, or ACO for short.
This node and edge graph brilliantly illustrates exactly how ACO works. Imagine you have a colony at node N and a food source over at node F. When our artificial ants first start searching for food, they just walk the graph randomly. But as they travel, they leave behind a chemical trail, a pheromone. Now, because pheromones naturally evaporate over time, the length of the path becomes the defining factor. The ants that happen to stumble onto a shorter path, well, they return faster, which means they lay down more pheromone on that specific path in the same amount of time. That stronger chemical concentration attracts more ants, which in turn lays down even more pheromone. It's an incredible feedback loop where very quickly the absolute shortest path emerges from the network.
If we break this down into pseudocode logic, the ACO meta-heuristic operates in 3 clear phases. Step 1 is the initialization phase, where we set up our artificial ants and variables. Step 2 is solution construction. Here, the ants traverse a graph representing your problem, say routing cities in a traveling salesman problem. They probabilistically choose their next node based on the existing pheromone levels. Then, step 3 is the pheromone update phase. Once the solutions are built, the paths that resulted in the best, shortest routes get their edge weights, meaning their pheromones, increased. And the bad, longer routes, those edge weights naturally evaporate. So, the secret sauce making all this work is a biological concept called stigmergy. And stigmergy is, honestly, just an elegant, indirect data broadcasting protocol. The ants aren't actually talking directly to each other at all. Instead, they are modifying the environment itself, and the environment holds the variable states. The probability of selecting a path directly increases with the amount of pheromone on that path. It's a completely self-reinforcing process.
Shifting gears now, let's look at Section 3, Bee Colony Optimization.
Now compare this to the ants. Notice the discrete role-based architecture here versus the ants' continuous flow. In a bee colony, you have 3 distinct groups of artificial bees: employed bees, onlooker bees, and scout bees. They each have highly specific jobs designed to thoroughly explore the solution space, which is represented here as different food sources.
Here is how the loop for artificial bee colony algorithms executes. Step 1. Employed bees evaluate the quality or the fitness function of a known food source by performing a local search around it. They exploit their memory. Once they finish, they head back to the hive to share that nectar data. Step 2. Onlooker bees wait in the dance area. They evaluate the shared information and then probabilistically select a food source to exploit. The higher the fitness value, the higher the probability an onlooker will choose it. Finally, Step 3. Scout bees handle the random exploration. If a food source is totally exhausted or abandoned, the employed bee assigned to it becomes a scout and just randomly searches the space for a brand new solution.
Let's put these two frameworks head to head. Ants rely on a pheromone trail. That's indirect communication with the environment, and it operates continuously as those trails fade and strengthen. Bees, however, use the waggle dance. This is direct communication between agents inside the hive, and it's highly discrete. An employed bee performs a dance that acts essentially like a data packet, directly broadcasting 3 specific pieces of data to the onlookers: the distance to the source, the direction, and the quality of the food.
All right, let's tackle Section 4, escaping the local minima.
Look, we're engineers. We know that conventional deterministic algorithms often converge on local optima, or just completely struggle with unknown search spaces. And while swarm intelligence aims to fix this, it still faces 2 main challenges. First, local optima. These algorithms can sometimes get trapped early by a good enough solution. An early super strong pheromone trail might actually blind the swarm to a globally better path sitting right nearby. Second is convergence speed. Because these agents are acting probabilistically and completely independently, waiting for the entire system to finally reach consensus on the absolute best solution can sometimes be a pretty sluggish execution process.
But here is the brilliant part. These algorithms literally natively debug themselves to escape those local minima. In ant colony optimization, they use pheromone vaporization and splashing. Vaporization naturally decreases pheromones on paths over time, right? This helps the system forget bad or suboptimal solutions it learned too early. Splashing does the exact inverse. It randomly adds to paths to force new exploration. In bee colony optimization, they use scout abandonment. There's a predetermined control parameter called the limit. If a position cannot be improved further through a set number of cycles, that food source is simply abandoned. The bees assigned to it become scouts and deploy for a completely random search. It effortlessly breaks out of the local minimum.
Which brings us to our final section, real-world engineering applications.
This isn't just theory, guys. Swarm algorithms are effortlessly solving complex scheduling and assignment problems at massive scale right now. Amazon uses swarm-inspired algorithms to coordinate thousands of warehouse robots simultaneously, each acting on local rules to route inventory and avoid collisions in real time. NASA is exploring swarm intelligence for distributed planetary mapping. It's way more efficient to have multiple small probes coordinate mapping than relying on one massive, slow rover. The military uses it for autonomous drone swarms that adapt their formation on the fly without central command. Telecoms use it to dynamically route network bandwidth, and cities are even using it for dynamic traffic management, where individual traffic signals act as independent agents to self-organize traffic flow and crush congestion.
So I want to leave you with this provocative thought. Take a hard look at your own architectures. Think about your dynamic, resource-constrained environments. Where could decentralized swarm algorithms, this literal brain of brains, replace the centralized bottlenecks in your tech stack? Could a digital ant colony or a swarm of bees be the exact optimization your next big project actually needs? Think about it. Thanks so much for joining me on this explainer. I'll catch you next time.